So you write some code, you click run, and magic, right? It just works. Well, what if I told you it's not magic at all, but a really fascinating secret journey your code goes on? In this explainer, we're going to pull back the curtain and follow your code step by step, from a simple text file all the way to a running program. Think about it. You've been slaving away on your C or C++ program. It's beautiful, it's perfect, you're so ready. You hit that glorious run button. And then what exactly? In that tiny sliver of time, there's a whole assembly line of tools that kicks into gear, working together to turn what you wrote into something the computer actually gets.
And here it is. This is the roadmap for our code's big adventure. It's a 5-step pipeline, and each stage has a very specific job. The preprocessor, then the compiler, the assembler, the linker, and finally, the loader. Let's dive in and see what each one of these really does.
All right, first stop on our journey is the preprocessor. Now, you can think of this guy as the prep cook in a busy kitchen. Its job isn't to cook the main meal, nope. Its job is to get all the ingredients, your source code, chopped, cleaned, and perfectly ready for the head chef, which is the compiler.
So, what's the first thing on the prep list? Cleanup. The preprocessor goes through and gets rid of anything the machine won't need. And that means all those super helpful comments you wrote for yourself and your teammates? Gone. Poof. They are absolutely essential for us humans, but to the computer, they're just noise.
Now, the other big job for our prep cook is handling directives. This is where it does a kind of find and replace. It looks for all your macros and swaps out the shorthand name with its actual value. It also handles file inclusions. So if you've included a header file, the preprocessor literally copy-pastes the entire contents of that file right into your code. And once the preprocessor's done its thing, our original file has been totally transformed. What comes out the other side is a brand new file, and it usually ends with a .i. This file contains what we call expanded code. It's clean, it's complete, and now it's ready for the main event.
Okay, now we get to the star of the show, the compiler. This is probably the tool you've heard of the most. It takes that expanded code and begins the first major translation. But wait, before it does anything, it acts like a bouncer at a club. It checks your code for any syntax errors. You forget a semicolon? Bam, you're not getting in. The whole process grinds to a halt right here.
So, assuming your code passes the syntax check, no typos, no missing semicolons, the compiler gets to work translating it into something called assembly code. Now, assembly is a very, very low-level language. It's kind of the bridge between our human-readable logic and the raw, fundamental instructions the hardware understands. And you guessed it. This step creates yet another new file. We're on a roll. Our .i file is now officially a .s file. That little .s at the end is our signal that the code has been successfully compiled down into assembly language. One more step closer. Next up in the assembly line is the assembler. This tool has one job, and one job only, but it is absolutely critical. It takes that assembly code we just made and performs the final translation into the computer's true native tongue. And what it spits out is called object code. This is it, folks, the real deal. We're talking pure binary, the actual zeros and ones that the computer's CPU was born to understand and execute. You might also hear this stuff called bytecode or machine code. It's all the same thing. And here's a cool little detail for you. The file that holds all this object code actually gets a different name depending on your operating system. If you're on Windows, you'll see a .obj file. But if you're on Linux or a Mac, you'll get a .o file instead. Same content, different label. We are so close. We're on the home stretch. Our code has been translated, it's fluent in machine speak. Now we just need to handle the final bits of packaging to get this show on the road. And that's where our last two tools come into play. First, the linker steps in. It's like the project manager. It takes our object file, grabs any other bits of code from libraries that it needs, and stitches them all together into one single, ready-to-run executable file. You know it on Windows as a .exe. Then, once that neat little package is ready, the loader, our final hero, takes that file and loads it into the computer's memory into RAM. And once that program is sitting in memory, that's it. It's showtime. The CPU takes over, starts grabbing those binary instructions one by one, and just goes. Your code is no longer text on a screen. It's alive. It's a running program. So when you step back and look at this whole thing, you see this huge divide, right? As the programmers, we can really only understand the code in its earliest stages, the original source file, and maybe the expanded .i file if we squint. But once a compiler works its magic, everything after that, the assembly, the object code, the final executable, that's all for the machine. And that's the whole secret life of your code. Now, knowing all this isn't just fun trivia. It's actually a super powerful debugging tool. The next time you get a really bizarre error message, you can stop and think about this journey. Ask yourself, where in this pipeline could things have gone wrong? Was it the preprocessor, the compiler, the linker? Thinking that way might just lead you straight to the answer.